So in this talk today, we want to introduce you a bit of what ESA does, because we guess that not many of you know. Who knows ESA? Hey. Wow! Much better than you, Mesa. Maybe I can go quick in this part. I can tell you which kind of data do we have. I mean, since we do a bunch of things, instead of going broad and tells you everything we do with the data analytics and with the visualization, what we did is something that we show a problem we are working on, and we show how we are progressing on it, and we hope to get your feedback on how to improve on that. So I tell you a bit about ESA. The first thing I want to point out is that it is an organization to promote exclusively peaceful purposes. So no satellite, spy satellite, or no military or anything. And all the focus is on space research, technology, Earth or interplanetary exploration. So we're going for the science and for the technology. Okay. ESA is everywhere. So, well, mostly in Europe, and we can basically from here. So it's in Darmstadt. So if you ever come to Darmstadt, you can come and pay a visit to us. And in Darmstadt is the ESOC, stand for European Space Operations Center. So we do space operations there, and operation is, how to say, if instead of a satellite would be a car, we would be the chauffeurs. So something for understanding, no? So we tell the satellite what to do, when to do, and when to send the data, what pictures to take, this kind of things, no? We work in the Red and myself. We work in the data analytics team for operations, and we focus mostly on this part here. When operating a spacecraft, we have this cycle. We plan what to do, we execute, we monitor that everything went fine, plan, execute, monitor. So for the data analysis part is more this monitoring part. So this a bit about ESA, and I want to tell you which kind of data we do have. So data we have are orbital data, for instance. I don't know if you follow the event of Rosetta and Philae and so. This is a picture from this, but I mean this applies to every satellite. In this case it was more complex. But we have position, velocity, orientation, all the eclipse information is we have there. We have mission planning data, so we know what the satellite should be doing at any point in time. We have ground station data. You know that we cannot communicate always with the satellite. We need to have visibility with the ground station, antenna like this. And we have all this data when is available and possibilities of communicating. Other data we have is, for instance, telecommand history, what we tell satellite to do, event packets. So when there is something asynchronous that is happening on the spacecraft inform us that this has happened. We have also mission control events, or mission control system events. What happens is that we have a ground software that takes care of automatically detecting if there are any issues with the satellite. So we have this. And the data that we use most is time series, so it's telemetry parameters. So satellite measures a bunch of things. So it measures the voltages of the batteries, or the speed of the reaction wheels, or the temperatures, currents, and all this is time series data in the same way like you would have a stock market shares prices. In the same sense, we have this kind of data. So these are for temperatures, yeah, all this in this case are temperatures. And in the problem that we want to present you today, is that we want to learn more about our data. So we have about 20,000 parameters like this, and we want to learn how they are interrelated. So which are the dependencies, so that in the future, if we are making an operation on a satellite that we know will affect some parameters, we want to understand beforehand which other parameter will be affected by that. Or if there is an anomaly, which are the candidate parameters that we need to look for causes for that. And we are looking for ways on how to visualize this information. So what we want to do is finding and visualizing these dependencies. And I'll give you an example. This was a problem that one of our flight control team engineers from Mars Express tell us. Said, well, you know, we have this time series corresponding to a temperature, and it start behaving very different here, there, and there. These are these changes that we don't understand why. Can you find some dependencies? The first thing we did is to have a technique to automatically detect changes. So our change detection can detect these changes, and then what we do is some probabilistic data mining approach, if you like, or data analytics, that we look for probabilistic dependence. So if the joint probability will be equal to the product of each one of the probabilities, we will say that it's independent. So we look something which is very dependent, so very different. So what we do is, why should we focus in only one parameter? Let's do for all and visualize this in a way that people can understand the patterns that they have in data. So this is what we're trying to do. Let's do for all. And how to visualize this? At the beginning we thought, we just show them a heat map. And this is what we got. This here you got the cause and the effect. So if you see a point, here is something. So I know that the cause for this will be around here, and this is the effect. But that was not too easy to follow. Nobody could read that because there are so many parameters. So we tried something a bit better, and we went for, guess what? We went for Excel. So at least you can read it. I mean, it's already better. So you have the cause, you have the effect. Here you have a 100% probability. You know, here you have 0.3. So it's improving, but we still believe there is a room for improvement in visualization. So we thought about, what about if we do a graph? And people can see the graph and understand the dependencies. So we did something like that. And based on this matrix, we said, well, we want to investigate this parameter. Let's have a graph with a level 1 dependency. So all the parameters that will be the cause for this. And I mean, it's a nicer way to see, but we lose the context. Because something we want to do is how this parameter depends on other parameters. So you have a broader view. And then say, well, that's easy. Let's do level 2. So we have level 1 and the dependencies of the others. And this is what we got. And maybe you don't see it, but this parameter is less than 1. Since it's too, let me just make a zoom. Yeah, that's the parameter. So there is a lot that we are losing, but it's more, this kind of representation is looking more on the way we want it to be. And Red joined us. He's a research fellow, and he's been working on, among other things, on visualization. And I think he can tell us what he's been working on.
Thank you, Jose. So Jose has worked a lot on this, and I tried to take a look myself and see, okay, if I were an operator, how could I link this one with this one? And I got lost because this is a static picture, you have to know. And so when you follow a line, you never know where it's sending, and you never know where it's going. So actually, you don't have the information. So should we really use a graph? So the thing with the graph, which is nice, is that you can maybe answer several questions. So, but what are the questions? First, an operator could tell you what are the dependencies of my parameter A. So you could draw them in a graph. That's quite nice. Of a parameter B, for instance. So you could also draw that. But what are the dependencies of those dependencies on B? I was like, okay, you can still draw them. But then you could also say, are those dependencies linked with those of A? So you could also see them in a graph. That's quite convenient. And also you can also answer the question, what are the links between subsystems? Because those parameters belong to subsystems. You know, you have solar arrays, you have batteries, you have reaction wheels, you have different things. And so you could also group them spatially, maybe that could be useful. So how to get all answers in one view, that's the question. And can we do that? Let's try. So the thing is, formalizing all this is answering all the question in one graph. Is what can I do with the graph? Is okay, I can use many different shapes. Those are simple one. And the edges also, I can have different weight in the edges, so they can mean different information. And also I can label, so in the node or out of the node, I can use different colors and also use the spatial distribution in a way that means something. I don't know what it means here, but it could mean something. So, and this spatial distribution is important for the overall understanding. So when you're just looking at 2 or 3 nodes, that's okay. But when you have like 100, 400, then okay, then what do I see here? Is it really relevant? So you have to take care of the algorithm you're choosing. Here is another one. So things are getting more spacey here, so I have more space. Maybe I understand more what's happening, but still, where are the links? It's not really clear. Then I get larger. It depends on what you want to achieve as a visualization. So what do you want to know? Is the back sufficient for what you want to achieve? Like what information you want to deliver? And for us, this could be one of the best one. So we tried to do that on the dependencies of Mars Express. So Jose has calculated the dependency over 6 months in 2015, and we got a huge file. And so we tried to cut to have only the most important dependencies. And here we used the graph and we used colors. We didn't use shape because semantically we have only parameters. So, and we used the colors to use the dimension of subsystems. So, for instance, do I have a laser here? Yeah, cool. So here in yellow you have the power system. So it's in yellow, and you see that you have a bit of yellow a bit everywhere because that's the main subsystem. And there you have like small red dots here, which are the attitude system. So they're not connecting to anything in this graph. Doesn't mean that it's not really connected in real life. So, but you have to take care how you interpret this. So when you zoom, you can have a different view. So meaning you have also a dimension in the zoom. So you can have the labels appearing. You can see clearly, well, a bit more clearly the links between the nodes. And also we found that it was convenient to have interaction with the graph in order to do more search and exploration on this. So the thing is that, is the graph the only solution? We have different concepts at our hands because we have different tools like D3GS, VizGS or whatever, and mostly in JavaScript. That's very useful. And which is mostly important is having interaction with the graph, because it's all about having the data, having more information about the situation, and searching and exploring in this information to try to find something meaningful. Because for operation, it's very important to know if there is a problem and where it's coming from, what's the real cause of everything. So we cannot really do it in a I would say a computational way, but we can improve the situational awareness of the operators with visualization. So today we're here, and that's really nice, so we can explore those visualization ideas with you. And so if you have feedback, we're always happy to listen. So if you have questions, you can talk to us.